thanks everybody for staying for the last keynote. And I know I'm between you and the recess, so I'll try to keep it on time. I hope I'm not going to be too techy. I'm going to talk more about technologies, and I hope it will still. It's not going to be code. It's not going to be code lines, but I hope it will still be interesting. The good news to start the morning with is the in-memory computing. It's here, it's strong, and it's growing. It's growing very fast, which means for people in the room, it's either you got more stuff to sell or you can leverage more technologies to help you, which is great. Is job security. I also hope to still have a job, not for the income, just for the fun of it. But if you try to classify what we're seeing in the in-memory space, you could really look at two key areas where you see people doing memory. And the first one is where you have applications that require very large amounts of memory in one server. You see people today deploying a single in-memory database, single system with dozens of terabytes of memory in it to keep all the data really in memory. We're talking big enterprises. You're seeing very big data, lots of memory. And the other class is where you can go distributed, okay? And people want to save money. So if you really, memory is what's holding you, okay? And you could distribute and use more nodes to have more memory in the nodes, but you're not taking advantage of the other stuff on the nodes, like the CPU capabilities that they have, thanks to Moore's Law that keeps on moving forward, and the networking backbone and so on. You might be wasting your money if you had more memory. So what's the state of the industry in all this? We've got the needs of the users, and how do we serve them? Well, for the in-memory in a single system environment, we're not really serving them that well. The DRAM, while becoming cheaper over time, actually is not keeping up with the growth of data. It would be nice. I don't have a slide like that, but if you look at how much memory pricing has decreased, like Abe mentioned before, and how much data has grown, we're actually not keeping up. Okay, so the single server having a dual socket, standard node that you could buy today, like every one of those, Dells and others sell, can max out at 700. If you're paying a lot for memory, expensive memory, it gets you to a terabyte or so, and that's it. That's it. You can't go bigger. If you want to buy some of the higher range systems, you could get to 6 and even sometimes 12 terabytes, and that's it. Anything beyond this, you're talking specialized things, cost a lot of money. Even the 12 terabyte options, a lot of money. Certainly not the credit card limit that Abe mentioned before. So we're talking about a sort of a glass ceiling. In the scale out, as opposed to the scale up in a single system, the scale out space, you got two major issues. The first is not every piece of software can be scaled out. Not everything, not every application, not every algorithm fits this. And a classic example is, okay, so we got this Oracle database that's running our system, our backend system, and we would like it to go faster. Let's just move the data to whatever. Any sort of in-memory, scale out, Spark, whatever. Well, it doesn't work that way. It's not a trivial task. It's not like, let's take the data out of the Oracle database and put it on this other NoSQL in-memory environment, and that's it, our application's good to go. It doesn't work that way, unfortunately, but it doesn't. And so some of the stuff can't be distributed, or it's not worth your business investment in distributing it. And the ones that you do distribute, they cost you money per the additional nodes that you put in. If you're using Amazon, you're paying for every instance that you're bringing up. If you have your own internal environment, you're paying for additional nodes, you're paying for maintenance and the IT staff that's there. And the last thing is, you get to hear some voices talking about alternatives, especially with the high-end storage devices, very fast storage devices, but they're no silver bullet either. So you're looking at an environment in which you have to explicitly program your application to say, well, this specific array, keep it in memory. This other array, you could put it on the fast disk. And oh, by the way, when you write to that disk, you have to do it this way and not the other way because I want the durability of the disk not to go away. We're talking SSDs and so on. So it's really not a silver bullet. There are some good technologies out there utilizing it, and it'll grow, but it's not one solution fits everything. So that's where the industry is. So we're poised for this great growth, and everything has to be fast, and everything has to be real time and get my answers now, and also everything has to be priced reasonably, but not everything is connected. And this is what we want to talk about today in software-defined memory. I'll mention software-defined computing and memory just for the sake of the whole picture. But in software-defined, I'm seeing different things than the audience is. Good, thank you. Software-defined computing, software-defined memory, what really is this? Well, we all know that we can create virtual computing environments, right? You do this with Zen on Amazon or VMware in your data center and so on. You could take what is really one piece of hardware and make it look like something completely different. You take one server and make it look like 20 small servers, for example. You could also do the opposite. You could take multiple resources and make them look like one. So we've been doing this in storage aggregation for years and so on. And so the first thing is software-defined computing, where you take many nodes, okay, turn them into one massive SMP, shared memory system, lots of cores, lots of memory. This is more of a supercomputing environment, so I'm not going to talk about it today, but it's there. It's been there for a while. But you can do pretty much the same with just memory. You could say, hey, I got adjacent nodes here in the rack. They got memory. I want this memory to be used by the application running on node number 1, and I don't care about the fact that the additional memory comes from node 2, 3, 4, 5, and so on. I want it to be transparent, and you can do that. So this is something that's been used already years, software-defined memory over fabric. Okay, and then, oops, back one, please. Well, okay, forward on that one, back on that one. Back. There's one more at the bottom of there. Sorry about that, guys. So I got to have 3 of them. Can you move forward so I have 3 of them on the right side? Excellent. And then, forget about the monitor. And then we have the software-defined memory over storage. Okay, we're basically the same memory pool that I've created with the adjacent nodes, I can create with high-performing storage inside my node. So I can take a system, put a lot of high-performing devices. Today it's Flash devices. Tomorrow it's Intel 3D XPoint and ReRAM and all those nice things that you can read up on the internet coming up for storage. No, I want it back. I didn't, okay? And the idea being is that these technologies are reducing price significantly. And with software-defined memory, they actually behave like memory. So you don't need to program for specific storage and so on. Okay, so we can do the magic. We can make it look like it's memory. Okay, even if it's memory over the fabric with some neighboring nodes, or if it's memory from storage. How well does it work? Well, first example I'm going to talk about is an in-memory commercial database. The example I'm going to show is actually based on data from a HANA deployment. And you got an application running using an 8-socket system. And using up all 6 terabytes of the machine. So we've got a decent, not very large, HANA database there, and record the throughput of application transactions. And we're not talking analytics here. HANA is, in addition to being an analytics database, is also a transactional database that you could do OLTP with. Well, what if you used, instead of that, software-defined memory over Fabric? Take just a quarter of the amount of memory on the server that has the compute capacity on it, and bring a memory pool from additional systems to compensate for the rest of the capacity. So you have really deployed 1.5 terabytes of memory, and then the rest of the 3/4 that are missing come from a data pool that you've put somewhere on your network, okay, from additional servers. Would be interesting to see what's the throughput of the transactions running in memory on a system like that. Well, the results are, they're not in yet. Results are not in. Next, please. Excellent. These are the results. So effectively, no difference in performance, okay? 2% is really not a difference. Now, of course, I'm not telling you that if you need 6 terabytes of memory for your in-memory database, okay, like HANA or others, I'm not telling you go buy specifically a server with less memory in it, but a big memory server overall. Just don't populate the memory and then bring up some memory from elsewhere. Obviously not. Either buy, if 6 terabytes are not enough for you, either buy the 6 terabytes with the server, or buy a small server. If you looked at your compute and you see that you're not really using those CPUs, buy a smaller server, less CPUs on it, much cheaper, and then bring in the memory from other servers. The thing is, we're talking about the specific client where we did all this benchmarking is actually a 30 terabyte client. And if you were to talk to someone, as early as 3 to 4 years ago, and say, look, to your IT department, or I need this 30 terabytes of data that I have, which is my phone records, whatever it is, organizations have a lot of data. I need it to be in memory, so please buy me a server that has 30 terabytes of memory on it. You'd get hospitalized, basically. They'll give you some good medicine and say, well, we're done. You certainly don't have a job anymore. And it's no longer that. The organizations do have that amount of data, and they do expect it to be in memory. They're investing a lot in those in-memory technologies, the software stack, HANA, and so on, Oracle. They cost money, and they expect to be able to do those things. So again, how well does it do? It does very well. It does great performance, allows you to scale. This technology scales to 2 petabytes of memory if you have the budget. Next example to talk about is on the scale out. So a Memcached web caching environment, a lot of web storefronts and content sites and so on use this technology. And we're looking at 500 G per node. So it's an environment where we try to maximize the amount of memory that we have on a node, and run a workload throughout time and see how many transactions we can run. And so first, take a system with 512 gigabytes on it. That's next, please. Okay, and compare that. Well, 512 gigs is a little bit expensive, so compare that with something more run-of-the-mill, 128 gigs. But I put a very fast NVMe SSD in there, or a few of them, to get very good storage and try to run the same exact workload. And as you can see, as the transactions roll, the swap kicks in on the SSDs, and performance starts to drop. And the more you allocate out of your overall pretty much random access cache for the Memcached, the worse your performance. You're losing about a half of your performance. Okay, so it may be cheaper. It's cheaper to buy the SSDs than the memory, but it's not really delivering what you want. Well, what if you take these same SSDs and treat them as software-defined memory of a storage? So you apply software-defined memory, same hardware, nothing changed. And you can't really see the additional line. Where's the laser? Because it's added here. Can you previous one, please? Just to see the change here. I don't know what happened now. Next. Forget about it. So believe me, it added a line here that's basically almost no different. Hey, 98%. Everybody likes this number. And so really, you haven't invested in any additional hardware, but you're using it the right way. You're using it as memory. That means you're dropping your I/O stack from the operating system. You're not doing any file system. You're not then doing any I/O per se. It's all virtualized. Looks like memory to the operating system. And you're gaining back all that performance. Now, you could be greedy, and you could say, hey, if that works well, why do 128 gigs? Let's go down. Okay, let's chop it some more. And so even if you go down to 64 gigabytes, so we're now doing a 1:8 ratio, 7/8 of your machine's memory is actually storage. It's high-end storage, but it's storage. And you're still getting decent performance. Sorry about that. I didn't mean that. I meant the laser. Can you back up? One more. Yeah, so you're talking about 7/8 of your memory coming from storage, not really memory, and still you're providing decent performance, roughly 80% of the performance of pure DRAM. Okay, that's where you want to go. You want to be able to drive performance, like Abe talked about before. You want to be able to drive performance, but you still want to do it in an economically efficient manner. You don't want to break the bank to have a lot of memory. So to summarize, basically, software-defined memory is going to be a solution people use to do in memory when they need to scale. It could be in order to scale and break the glass ceiling, so we have a single server with a lot of memory on it, or to be able to reduce cost, and instead of having 10 racks deployed, only have 4 racks deployed, because the overall memory you could put in them is going to be the same. Okay, and really that's your blocking factor. That saves you money. We've got technology that does all this high-end virtualization. We've been doing this for more than a decade. We've got the software-defined memory over fabrics used by clients for close to 5 years now, very successfully around the world. The 30 terabyte example I gave you before is nothing new, okay? So, and we've got multiple of them. So this is working very nice, and it's again, the scale you could reach with a single server, up to 2 petabytes of memory, of actually DRAM made into one pool, which is, okay, we haven't seen anybody need that, so we're future-proof on that. And you could go up to 128 terabytes on the software-defined memory over storage. That means you buy a server big enough with enough PCI lanes and you plug enough high-end storage into it, enough non-volatile storage into it, you could get to that high of a memory and keep everything in memory very cost effectively. The software-defined memory over storage is going to be shipped via our partners. So that is something that basically go buy from the NVM vendors, the non-volatile memory vendors, as an add-on. They have a drive that is a storage drive, and they have a drive they give you. It's a memory drive. You plug it in, and although it's storage drive, it appears in the system to be as if you've added memory. With that, I end. It's not many seconds left, so thank you very much.